This is Module 5 continuous time Markov chain. In the first lecture, we have discussed the definition of a continuous time Markov chain. Then we have explained how we can derive the Chapman-Kolmogorov equation. Then we have defined infinite decimal generator matrix. Then I have given the Kolmogorov differential equations in the first lecture. In the lecture 2, I am planning to discuss the limiting distribution, stationary distribution and steady state distribution. Followed by that, I am planning to give a description about the birth death processes and also some simple examples for the limiting distribution, stationary, steady state distributions and birth death processes. Before I go to the limiting distribution, let me give the example for the continuous time Markov chain to get the time dependent solution. This example is the very simplest example, that is a two states continuous time Markov chain. The default one is a time homogeneous. The state space are 1 and 0. 1 you can consider as up state or operational state, and 0 is a down state, non-operation state. So this can be visualized for the any model in which the whole dynamics can be described with the two state and the Markov property is satisfied. The system going from the state 1 to 0, or the time spending in the state 1 before moving into the state 0, that is exponentially distributed with the parameter lambda. Once it is failed, that means the system is in the down state, the time spent in the repair time, that is exponentially distributed with the parameter mu. So once the repair is over, the system is operation state, therefore it is in the up state. So the 0 is related to the down state and 1 is related to the up state, and the mu is nothing but the mean. 1 by mu is the mean time for the repair, and 1 by lambda is the mean time of a failure, and the failure time is exponentially distributed with the parameter lambda, and the repair time is exponentially distributed with the parameter mu. This is a state transition diagram for the two state CTMC. The corresponding Q matrix, the infinite decimal generator matrix, that consists of it's a 2 cross 2 matrix. The system going from the state 0 to 1, that rate is mu. The system is going from the state 1 to 0, that rate is lambda, and the diagonal values are minus of summation of other values, that row sum. So 0 to 0 is minus mu and 1 to 1 is minus lambda. Therefore the rates are in the other than diagonal elements, and the diagonal elements are minus of sum of the row values other than that diagonal element. So this is nothing but in a very small interval of time delta t, the system is moving from the state 0 to 1, that probability, the probability of system moving from the state 0 to 1, that is nothing but the down state to the up state in a very small interval of time delta t. Why we are finding the probability of delta t? Since the model is a time homogeneous, only the interval is matter, not the actual time. Or you can visualize this as the some time t to t plus delta t also. So this is the interval of delta, small negligible interval delta t. The system is moving from the state 0 to 1, that probability is nothing but the rate, mu is the rate, is nothing but the repair rate. So the mean rate mu times the delta t plus order of delta t. It's a small o. Order of delta t means as delta t tends to 0, the order of delta t will be 0. Similarly, you can visualize the probability of system moving from the state 1 to 0 in the interval delta t, in a small interval delta t, that is same as the failure rate lambda times the delta t, that is a small interval of time, plus order of delta t. So, this order of delta t also tends to 0 as delta t tends to 0. So, using this I can make the forward Kolmogorov equation. I can go for writing a forward Kolmogorov equation or backward Kolmogorov equation, but forward Kolmogorov equation is easy to make out. So, if the system is in the state I at time 0, what is the net rate? The system will be in the state 1 at the time t. That net rate is nothing but what are all the inflow, that probability rate minus what are all the outflows. That is the way you can visualize the right hand side. So, all the positive terms are related to the incoming rates, and all the negative terms related to the outgoing rates. So, since it is a two state model, if the system is in the state 0 at time t, there is a possibility it is not moved anywhere from the state 0, or it would have come from the state 1. Therefore, the incoming will be the state 1. Therefore, the system will be in the state 1 at time t, and starting from, given that the starting from the state I, that probability multiplied by the rate sort of inflow minus, because we are writing the equation for the state 0, therefore, it is not moved from the state 0, that is with the rate mu it can move to the state 0 to 1. Therefore, minus mu times, it does not move from the state 0, therefore, minus mu times the probability of being in the state 0 at time t, given that it was in the state I at time 0, that probability multiplied by minus mu, that is a outflow, and the lambda times pi 1 t, that is a inflow. Therefore, the left hand side it is a derivative of the function t, it is a probability function. So, pi 0 dash t, that is nothing but the net rate being in the system at time 0, sorry, at time t in a state 0, given that it was in the state I at time 0, that net rate is same as a inflow minus outflow with the corresponding rates. Similarly, you can write the equation for the state 1. That means you start from the state 1, either you would have come from the state 0 to the 1, or you did not move from the state 1. Therefore, minus lambda times pi 1 of t plus mu times pi 0 of t, that is the net rate corresponding to the state 1. So, now we are able to write the forward Kolmogorov equation. So, this is the interpretation of the forward Kolmogorov equation. You can write easily by making a matrix Pij of t dash, that is equal to Pij of t times q, where q is the infinitesimal generator matrix. Then also you will get the same thing. So, I am just giving the interpretation. Now, my interest is to find out the time dependent or transient solution for this two state CTMC. For that, this is a differential equation. We need an initial condition to solve these equations. So, I make the assumption at time 0 the system is in the state 1. Therefore, the transition probability of system, the P11 of 0, that is equal to 1. Since I made the assumption the system was in the state 0 at the state 1 at time 0, therefore, that the being in the state 0, that is going to be 0. So, I need this both the initial conditions to solve the equation. So, let me start. Since I made the initial condition state is 1, therefore, I is equal to 1. So, I will have the first equation, that is I always have the summation of the probability at time t. These transition probabilities are going to be 1, the summation, and also I have two differential equations. So, what I can do, I can take the second equation in this, then instead of P10 of t, I can use the summation of probabilities equal to 1. Therefore, instead of P10 of t, I can use the P10 of t is nothing but 1 minus P11 of t. I can substitute in the second equation. Therefore, I will get P11 dash of t is equal to minus lambda plus mu times P11 of t plus mu. Substituting P10 of t is equal to 1 minus P11 of t in the second equation, the previous slide. Now, I have to solve this differential equation. The unknown is P11 of t. Conditional probability. I have to use the initial condition P11 of 0 is equal to 1. Using that, I will get P11 of t is equal to mu divided by lambda plus mu plus some constant e power minus lambda plus mu times t. That constant I can find out using this initial condition. Therefore, k is equal to lambda divided by lambda plus mu. So, the P11 of t is equal to, substituting k is equal to lambda divided by lambda plus mu in this equation, I will get the P11 of t. Once I know the P11 of t, use the first equation. So, I will get P10 of t is equal to 1 minus P11 of t. Therefore, P10 of t, that is equal to this expression. You can cross check now. If you add both the equations, you will get 1, and if you put t equal to 0, you will get the initial condition also correctly. And if you put t tends to infinity, that we are going to discuss in the limiting distribution, if you put t tends to infinity in this expression, you will get mu divided by lambda plus mu, lambda divided by lambda plus mu. So, this is for the t tends to infinity. Therefore, if you make a matrix, the limit n tends to infinity of limit, if you find out the limiting distribution of limit t tends to infinity of p I j of t. So, you will get the matrix, and this matrix has a t tends to infinity. For this example, it is a 2 cross 2 matrix, and that consists of for different values. So, you will have a for now we are doing for the second row. Therefore, that is equal to lambda divided by lambda plus mu, and and this is equal to mu divided by lambda plus mu. So, if the system start from the state 1 at a t tends to infinity, the system will be in the state 0 with the probability lambda divided by lambda plus mu, and the system will be in the state 1 with the probability mu divided by lambda plus mu. Similarly, if you go for I is equal to 0, you will get the same derivation, and you can fill up what is the element here. So, this is the limiting distribution probability matrix, and if you see that the rows are going to be identical. So, you will have the same identical rows in this row also. So, that means you will get the limiting distribution. I will discuss the limiting distribution in the after giving the one more example. I will explain in detail. So, this is the transition probability system starting from the state 1 and being in the state 1 or 0 at a time t. I am going to give one more example. This has 3 states, and this is a state transition diagram, and the values are nothing but the rates in which the system is moving from one state to other states. So, that is the difference between the state transition diagram of DTMC and the CTMC. So, this is the rate in which the system is moving from one state to another state, and some arcs are not there. That means there is no way the system is moving from the state 2 to 3 in a small interval of time, whereas all the other possibilities are I have given. So, the corresponding Q matrix is a 3 cross 3 matrix, and you can make out all the row sums are going to be 0, and the diagonal elements are minus of sum of other values in the same rows, and other than the diagonal elements the values are greater than or equal to 0. My interest is to find out the time dependent solution for this example also. I can make a forward Kolmogorov equation, p dash of t is equal to p of t times q. it's a 3 cross 3 matrix, therefore I will have a 3 equations, and I have one equation. I can have a summation of probabilities equal to 1, and I can start with the initial condition, the system being in the state 1 at time 0, that probability is 1. I can start with that, and I can solve those 3 equations with the initial condition, and I can get the solution. That is a one way. Since it is a finite state CTMC, there are many ways to get the time dependent solution. Basically, you have to solve the system of differential equations with the initial condition. Here I am using the eigenvalue method. That means find the eigenvalues for the Q matrix. Therefore, use the eigenvalue and eigenvector concept and get the P11 of t with the unknowns k1, k2, k3. And to find the unknowns k1, k2, k3, use the initial condition. Here I am using the initial condition as well as the Q matrix values. The Q11, that means the element corresponding to the 1, 1, that is nothing but the P dash of 1, 1 of 0. Similarly, if I go for Q square matrix and Q11 of 2, the element in the 1, 1 in the Q square matrix, that is nothing but P double dash of 1, 1, 0. Therefore, now I can use these 3 initial conditions to get the unknowns value k1 and k2, k3, k1, k2 and k3. So, once I know the k1, k2, k3, I can substitute. Therefore, the P11 of t is equal to this much. Similarly, I can go for finding the P1, 2 of t and P1, 3 of t. I do not want P1, 3 in the same way, because once I know the P1, 1 of t and P1, 2, t. So, 1, 3, t is nothing but 1 minus of those two probabilities, because the summation of probability is equal to 1. So, this is the other way of getting the time dependent solution, the transition probability of system being in the state j, given that it was in the state I at time 0. Suppose the CTMC has the finite state space, then I can use the exponential matrix also to get the time dependent solution. That is what I have given this way. So, start with the forward equation. Therefore, the solution is going to be P of t is equal to P of 0 e power q of t. P of t is the matrix, P of 0 is the matrix, e power qt, that is also again going to be a matrix, exponential matrix. Therefore, I am writing e power qt is nothing but q is the matrix and the t is the real value. So, greater than or equal to 0. Therefore, e power qt is going to be the I matrix. I matrix is nothing but the identical matrix of order whatever the state space number, plus the summation I is equal to n is equal to 1 to infinity of q power n times t power n divided by n factorial. So, that the whole thing is going to be the exponential matrix, and using that you can get the P of t. That is a, I am not going detailed for how to compute this e power qt and so on, but whenever you have a CTMC with a finite space, through this method also one can get the time dependent solution. So, with this I have completed the examples for the CTMC to find out the time dependent or transient probabilities. Now, I am moving into the limiting distribution. The way we discuss the limiting distribution for the CTMC, the same concept can be used for the CTMC also. The change is instead of the one step transition probability matrix, here we have to use the infinite decimal generator matrix in a different way. So, I am first giving the ergodic theorem. Whenever the CTMC is irreducible, that means all the states are communicating with all other states. Since all the states are communicating with all other states, if one is of the particular type, it is a positive recurrent, then all the other states are going to be a positive recurrent. If one is going to be a null recurrent, then all the other states also going to be a null recurrent. So, here I am making the assumption the CTMC is irreducible as well as all the states are positive recurrent. Then the limiting distribution always exists. Suppose it is independent of an initial state, it need not be a independent of initial state. Suppose the same thing is independent of initial state, then I can write that limiting probability is a Pij of t. Since it is independent of I can write it as the pi j. Then I can form a vector, and since it is a limiting distribution, it is a probability distribution. Therefore, the probabilities are, these probabilities are always greater than or equal to 0, and the summation of probability is going to be 1. It will not be defective, it will not be less than 1. That is ergodic theorem says. Whenever you have a irreducible CTMC with all the states are positive recurrent, then as a t tends to infinity, the system has the distribution, limiting distribution. If it is independent of initial state, then you can label with the pi j as the probabilities, and this probability distribution satisfies it's a probability mass function. Therefore, it satisfies the probability mass function conditions. That means whenever you have a dynamical system in which it is a irreducible model and all the states are positive recurrent, that means the mean recurrence time is going to be a finite value, then that system is called it as a ergodic system, or the ergodic the concept can be used. Therefore, as a t tends to infinity, you can get the limiting distribution. If it is independent of initial state, means whatever be the seed, you are going to do it for the discrete event simulation for the dynamical system, that is ergodic, for a ergodic system, then the initial condition seed does not matter to get the limiting distribution. Later we are going to give some few examples how to find out the limiting distribution. I am explaining the stationary distribution also. The stationary distribution, the way I have explained the DTMC, the way I have discussed the DTMC, the CTMC also same. So, I have a vector. If the vector satisfies these three conditions, probabilities, therefore greater than or equal to 0, summation is equal to 1, and you should be able to solve this equation and get the pi's. It is a homogeneous equation. So, you need a second condition to have the non-zero probabilities. So, if you solve pi q is equal to 0 along with the summation of pi j is equal to 1, and if these pi j's exist, then the CTMC has the stationary distribution. The similar way I have discussed the stationary distribution for the DTMC model also. Instead of pi q is equal to 0, we had a pi p is equal to pi. So, if any vector satisfies that pi p is equal to pi and summation of pi a is equal to 1 and all the pi a's are greater than or equal to 0, then that is going to be a stationary distribution for DTMC. The same way, if pi q is equal to 0 and pi summation of pi j is equal to 1, pi j's are greater than or equal to 0, if this is satisfied by any vector, then that is going to be the stationary distribution for a time homogeneous CTMC. Every time we are discussing the default CTMC, that is a time homogeneous CTMC. The main result for the stationary distribution, whenever you have a irreducible positive recurrent CTMC, the stationary distribution exists and that is going to be unique. Whenever the CTMC is a positive recurrent as well as irreducible. There is no need of periodicity in the CTMC, whereas the same stationary distribution, the stationary distribution for the DTMC, we have included one more condition, that is aperiodic. But for the CTMC, there is no periodicity for the state. Therefore, as long as the system is irreducible and a positive recurrent one, then the stationary distribution exists and it is unique. And by solving these equations, you can get the unique stationary distribution. The way I have explained the time reversible concept in the DTMC, the CTMC also has the time reversible concept. So, the time reversibility equation is a pi I times qij is equal to pi j times qji. The q's are nothing but the rates and the pi's are nothing but the probability values. So, if pi i's exist, this is stationary probability or stationary distribution exist, then if the stationary distribution exists as well as the time reversibility is satisfied by CTMC, then that CTMC is a positive recurrent, and you can say that it is a time reversible, and the solution pi is nothing but the stationary distribution. So, this result says for irreducible CTMC, if there exists a probability solution pi satisfy the time reversibility equation. This is a time reversibility equation where q's are rates, pi's are the probability solution. If it is satisfied by the irreducible CTMC, the time reversible equation, then that CTMC has a positive recurrent states, and that CTMC is called the time reversible, as well as the pi is called the stationary distribution. So, initially we have not taken as a stationary distribution, some probability solution satisfies the time reversibility equations and it is a irreducible CTMC, then that CTMC has a positive recurrent states and pi is nothing but the unique stationary distribution. So, the usage of this concept is whenever any CTMC is first it is irreducible and satisfies the time reversibility equation of this form, then you do not want to solve pi q is equal to 0 and the summation of pi a is equal to 1 to get the stationary distribution. Instead of that, use this time reversibility equation instead of solving pi q is equal to 0, and then use a summation of pi a is equal to 1 to get the one unknown. That means use the time reversibility equation repeatedly, recursively, and get all these in terms of one unknown, either pi naught or pi 1, whatever it is. Then use the summation of pi a is equal to 1 to find that unknown instead of solving pi q is equal to 0. So, whenever it is model is irreducible and time reversibility equations are satisfied, then you can conclude all the states are positive recurrent and you can find pi the stationary distribution in an easy way instead of solving pi q is equal to 0. I am going to give one simple example what is the limiting and stationary distribution. Take the two state CTMC and we know that Q matrix, and you can verify whether this is going to be irreducible and a positive recurrent, since it is a finite state model and both the states are communicating each other. Therefore, it is a irreducible positive recurrent states. So, you can solve pi q is equal to 0 and the summation of pi a is equal to 1. So, pi times q, pi is the vector, q is the matrix and again 0. Therefore, if I take the first equation, I will get minus mu times pi naught plus pi lambda times pi 1 is equal to 0 by taking the first equation, minus mu pi naught plus lambda times pi 1, that is equal to 0. From this I can get the pi 1 in terms of pi naught. Since it is a homogeneous equation, I have to use a one non-homogeneous or normalizing condition, summation of pi a is equal to 1. So, using that I will get pi naught is equal to lambda divided by lambda plus mu. Once I know pi naught, then pi 1 is equal to mu divided by lambda plus mu. So, this is the stationary distribution as well as the limiting distribution, because it satisfies both the conditions. Take the second example. Second example also finite state model. All the states are communicating with all other states. Therefore, it is a irreducible. Since it is a finite state model, you won't have a null recurrent. It's a positive recurrent model. So, I can solve pi q is equal to 0 and the summation of pi a is equal to 1. So, there are 3 equations. So, I take the first 2 equation and one normalizing equation and solve these 3 equation, I can get pi 1, pi 2, pi 3. You can verify that the summation is going to be 1. So, this is the limiting distribution as well as the stationary distribution, because the model is the irreducible positive recurrent model. So, this limiting distribution and the stationary distributions are one and the same. Instead of solving pi q is equal to 0, you can use the time reversibility, but before that we should verify whether the time reversibility equations are satisfied by this model. If this model satisfies the time reversibility equation for all I, comma j, then you can conclude it is a time reversible Markov chain and so on. But example 1 is a time reversible Markov chain, whereas that example 2 is not a time reversible Markov chain. You can verify it. Now I am moving into the special case of a continuous time Markov chain, that is a birth death process. This is a very important time homogeneous continuous time Markov chain, because many of the scenario can be mapped with the birth death process, either with the finite state or infinite state. Let me first give the definition of a birth death process. I started with a continuous time Markov chain, that is a time homogeneous continuous time Markov chain with the state space countably infinite. It can be a finite also. That CTMC is going to be called it as a birth death process if there exists a constants lambda i's and mu i's such that, and these are all nothing but the infinitesimal generator matrix elements, and this is I to I plus 1, that rate is always lambda I, and the rate in which the system is moving from the state I to I minus 1, that rate is mu I, and the diagonal elements are minus of lambda I plus mu I, whereas all the other rates the system is moving from the state I to j other than I to I plus 1, I to I minus 1 and I to I, and all other rates are always 0. Absolute of I minus j is greater than 1. That means you will have the infinitesimal generator matrix in which you will have only have a diagonal matrix, tridiagonal matrix, and all other elements are going to be 0. I can write down the condition so that it will end up the rates are going to be only lambda i's and mu i's, so on, not all other rates are going to be 0. So, if I start with I is equal to 0, the system is moving from the state 1 to 0 in the interval of delta t, because it is a time homogeneous model. So, this is nothing but this probability, the system is moving from the state 1 to 0 in the interval of delta t, that is nothing but the rate is mu 1 times delta t plus order of delta t. Similarly, the system is moving from the state 0 to 0 from the time t to t plus delta t or during the interval delta t, that is nothing but 1 minus lambda naught times delta t plus order of delta t. So, these mu i's and the lambda naught and so on, these values are always going to be greater than or equal to 0, strictly greater than 0 also. For I is greater than 0, the system is moving from the state I to I, that is 1 minus lambda I times delta t minus mu I times delta t plus order of delta t, whereas the system is moving from I plus 1 to I, one step backward, that is mu times I plus 1 delta t. The system is moving from the state I minus 1 to I for I is greater than 0, that is a forward one step move, that is lambda times I minus 1 delta t plus order of delta t. This order of delta t, it may be a function of delta t, it need not be the same. As a t tends as delta t tends to 0, these quantities are going to be 0. Order of delta t divided by delta t is going to be 0. Therefore, this is the way the system is moving from the one state to either one step forward or either one step backward or move anywhere. So, these are all the only 3 possibilities with these probabilities. Therefore, we land up the Q matrix is going to be the system is moving from the state I to I plus 1 forward one move, that rate is lambda i's, and the system is moving from the I to I minus 1 one step backward, that is mu I, or the system being in the same state, that rate is minus lambda I plus mu I. Therefore, there is no other move from the system from one state to all other states, either one step forward or one step backward. So, this can be visualized in the state transition diagram. Since I started with the state space 0 to infinity, there is a possibility you can have a label from some negative integers to the positive integers. So, you can always transform into something. Therefore, default scenario or the simplest one I discussed from 0 to infinity. Therefore, you can visualize whatever be the label that can be transferred in a one-to-one fashion. So, this is the rate in which the system is moving from the state 0 to 1, that rate is lambda naught. The system is moving from the state 1 to 2, that rate is lambda 1, or the system is moving from the state 1 to 0, that rate is mu 1. Therefore, the time spent in the state 1 before moving into any other states, that is a minimum of the time spending in the state 1 before moving into the state 2, or the system time spending in the state 1 before moving into the state 0. So, both are exponentially distributed with the parameters lambda 1 and mu 1, and the minimum of that time is the spending time or the waiting time in the state 1, that is going to be exponential distribution with the parameter lambda 1 plus mu 1, because both are independent. The time spending in the state 1 before moving into the state 2, and similarly the time spending in the state 1 before moving into the state 0, and both the random variables are independent, that is assumption. Therefore, it is going to be a exponentially distributed random variable, the time spending in the state 1, that is exponential distributed with the parameter lambda 1 plus mu 1. Like that you can discuss for all other states. So, whenever you have a birth death process, the system either move one step forward or one step backward, then it is called a birth death process. Therefore, here these lambda i's are called the system is moving from one state to forward one step. Therefore, these lambda i's are called the birth rates. The system is moving from one state to the previous one state, and the corresponding rates mu i's, mu 1, mu 2, mu 3 and so on, and these rates are going to be called it as a death rates. So, lambda i's are nothing but the birth rates. That means the rate in which the system is moving from the state I to I plus 1, that depends on I. Therefore, that rate is lambda I. The system is moving from the state I to I minus 1, that is related to the death by 1, that is a function of I. Therefore, that death rate is mu I. So, the lambda i's are the birth rates and the mu i's are the death rates. Therefore, this is suppose example, the system moving from the state 2 to 1, the death rate will be mu suffix 2. So, you can fill up the Q matrix. If you see the Q matrix, it is a tridiagonal matrix. So, here I am giving few examples for the birth death process. The first example consists of is a finite state model. The birth rates are lambda naught, lambda 1 till lambda n minus 1. The death rates are mu 1, mu2 and mu_n. It is a finite state birth death process. The second example is the infinite state birth death process. The third example, all the death rates are 0, that is also possible. The fourth example, all the birth rates are 0, that is also possible. But you can discuss the one can discuss the state classification also. The first one, it is a finite state model, all the states are communicating with all other states, therefore it is a irreducible positive recurrent birth death process. The second one, it is a infinite state, all the states are communicating with all other states, it is irreducible, but one cannot conclude without knowing the values about the lambda naughts and lambda i's and the mu i's, one cannot conclude it is a positive recurrent or null recurrent. If the mean recurrence time that is going to be a finite one, then you can conclude it is a positive recurrent, otherwise it is null recurrent. So, as such one cannot discuss now the positive recurrent or null recurrent, but you can conclude it is a recurrent state. The third example, the system is keep moving forward, therefore all the states are transient states. It is not irreducible, it is a reducible model, all the states are transient states. That means as a t tends to infinity, the system will be in the some infinite state. So, one cannot define an infinite state, therefore the limiting distribution will not exist in this situation. The fourth example, it is a finite model, but all the states are not communicating with all other states, therefore it is not a irreducible, it is a reducible model. Whenever the system starts from some state other than 0, over the time the system is keep moving backward, and once it reaches the state 0, it will be forever. Therefore, state 0 is the observing barrier. State 0 is the observing state, and all other states 1 to n, those states are the transient states. The limiting distribution exists, the system will be in the state 0 at t tends to infinity with the probability 1, and all other states are transient states, therefore the probabilities are 0. We are discussing the forward Kolmogorov equation for a special case of continuous time Markov chain, that is a birth death process. For a birth death process, the Q matrix is a tridiagonal matrix, therefore you will have the equations from the forward Kolmogorov equation, you will have only 2 terms in the right hand side for the first equation, and you will have only 3 terms, the diagonal element and 2 off diagonal elements. Therefore, the second equation one can, the first equation one can discuss first. The p dash of I comma 0, that is nothing but the system is not moved from the state 0, moving from the state 0, that rate is lambda naught, therefore not moving minus lambda naught times the probability, and or the system can come from the state 1 with the rate mu 1, therefore mu 1 times p I comma 1 of t. For all other equations, either the system comes from the previous state with the rate lambda j minus 1, or it comes from the forward one state with the rate mu j plus 1, or not moving anywhere. So, these are all possibilities. Therefore, with these 3 possibilities you have 3 terms in the right hand side, and that is the net rate for any state j. So, if you solve this equation with this initial condition Kronecker delta I comma j, you will have the solution of a p I comma j. Here I am discussing the steady state distribution. The way I have discussed the limiting distribution, that is a limit t tends to infinity, probability of I comma j of t exists, then it is called the limiting distribution, and the stationary distribution is nothing but for the DTMC it is a pi p is equal to p, summation of pi a is equal to 1, for the CTMC it is pi q is equal to 0, and the summation of pi I is equal to 1, that is going to be the steady state distribution, stationary distribution. Now I am discussing the steady state distribution, that is nothing but when t tends to infinity, the birth death process may reach steady state or equilibrium condition. That means the state probabilities does not depend on time. That is the meaning of a steady state distribution. As a t tends to infinity, whenever we say the birth death process reaches a steady state or equilibrium, that state probability does not depend on time. That means if a steady state solution exists, since the state probabilities does not depend on time t, the derivative of the time dependent state probability at time t, that derivative at t tends to infinity becomes 0 if the steady state solution exists. Since the state probabilities does not depend on time t as a t tends to infinity, I can write as a pi i's limit t tends to infinity of pi I of t. So, this is different from the way we discussed earlier, that conditional probability p I j of t. But using p I j of t, one can find out what is pi I of t. That is nothing but the pi I of t that I have given in the first lecture for the CTMC. The pi I of t, that is nothing but what is the probability that the system will be in the state I at time t. That is same as what is the probability that the system will be in the state I given that it was in the state some k at time 0 multiplied by what is the probability that it was in the state k at time 0. That is nothing but summation of k, and this is nothing but the transition probability, and this is nothing but the initial probability vector element. So, using pki of t or pij of t, that is a conditional probability, one can get the unconditional probability. This is nothing but the distribution of x of t. So, this is a probability mass function, probability mass at state I. So, now what I am defining, whenever the steady state distribution exists, that means it is independent of time t. Therefore, as a t tends to infinity, the pi I of t can be written as the pi I, and whenever the steady state solution exists, I can use a limit t tends to infinity, the derivative of a pi I of t, that is going to be 0. Therefore, I am going to use these two to get the steady state probabilities for the birth death process. Since as a t tends to infinity, the derivative of pi aj of t is equal to 0, therefore, all the left hand side in the forward Kolmogorov equation, that is going to be 0. The right hand side you will have as a t tends to infinity, the pi I of t, that can be written as the pi 0 and the pi 1. So, the way we write the conditional probability for Pij with the Kolmogorov forward equation, you can write the similar equation for the unconditional probability pi i's also. So, now I am putting the left hand side zeros because of this condition, limit t tends to infinity, the derivative is equal to 0, and the right hand side I am using as a t tends to infinity, this probability is nothing but the pi i's. Therefore, it is going to be minus lambda naught times pi naught plus mu 1 times pi 1, and all other equation has 3 terms, and this is a homogeneous equation, and you need one normalizing condition. So, from this homogeneous equation I can get recursively pi i's in terms of pi naught. So, from the first equation I can get pi 1 in terms of pi naught, and the second equation I can get pi 2 in terms of first pi 1, then I can get pi 1 in terms of pi naught. Therefore, recursively I can get pi i's in terms of pi naught for all I greater than or equal to 1. Now, I can use the normalizing condition, summation of pi I is equal to 1. Therefore, I will get pi naught is equal to 1 divided by summation of this many terms in the product form. Since we need steady state probabilities, and all the pi i's are in terms of pi naught, as long as the denominator is converges, you will have a pi 0 is greater than 0. Once pi 0 is greater than 0, then we will get all the pi i's with the summation of pi is equal to 1. So, whenever this series converges, then I will have a steady state distribution with the positive probability, and the summation of probability is going to be 1. So, this is the condition for a steady state distribution for a birth death process, because we started with the birth death process forward Kolmogorov equation. Using these two conditions, we have simplified into this form and use the normalizing condition and get the pi naught. As long as the summation is or the series is converges, then we will have the steady state. If the series diverges, that means by substituting the values for the lambda i's and mu i's, and if the series denominator series diverges, then the pi naught is going to be 0. In turn, all the pi i's are is equal to 0. Therefore, the steady state distribution won't exist if the denominator series diverges. I am going to give a one simple result for a irreducible positive recurrent time homogeneous CTMC. We know that the limiting distribution exists, a stationary distribution exists. Now, I am including the steady state distribution also exists. I have given for a steady state distribution for the birth death process, not for the CTMC, but here I am giving the result for the CTMC. All the three distributions exist and all are going to be same. Whenever the CTMC is a time homogeneous irreducible positive recurrent, all these three distributions are same, and one can evaluate, one can solve these two equations, pi q is equal to 0 and with the summation of pi a is equal to 1, you can get the limiting distribution, stationary distribution, or steady state or equilibrium distribution. As a special case of birth death process, I am going to discuss these two processes in this lecture. Whenever we say the birth death process is a pure birth process, that means all the death rates are going to be 0. We started with the birth death process with the only lambda i's are greater than 0 and the mu i's are going to be 0, then it is going to be called as a pure birth process. There is a one special case of pure birth process with the lambda i's are going to be constant, that is lambda, that is a Poisson process, that I am going to discuss in the next lecture. And in this pure birth process, these lambda i's are the function of I. Here all the states are transient states. Here I am discussing the pure death process. A birth death process is said to be a pure death process if the birth rates are 0 and the death rates are non-zero. In particular, we shall obtain the time dependent probabilities of a pure death process in which the death rates mu i's are equal to I times mu. As I given the example, as a fourth example in the birth death process, this state 0 is a observing barrier. Therefore, the state 0 is a observing state and all other states are going to be transient state. And here the limiting distribution exists, and one can also find the time dependent probabilities for this model. Suppose you start with the assumption the system at time 0 in the system is in the state n. At time 0, the system is in the state n at time 0. With that assumption, I can frame the equation, that is a pi n dash of t is equal to minus n times mu of pi n of t. That means the rate in which the system is in the state n, that is nothing but not moving to the state n minus 1 with the rate n minus n times mu. Therefore, the equation for the state n, that is a pi n dash of t, that is equal to not moving from the state n, therefore minus that outgoing rate, that is n times mu, being in the state is n, therefore pi n of t. I can use the initial condition pi n of 0 is equal to 1, so I will get pi n of t. For the second equation, I have to go for what is the equation for the state n minus 1. So, the pi n minus 1 dash t, that is nothing but either the system come from the state n or not moving from the state n minus 1. Therefore, system coming from the state n, that is n mu times the system being the state n minus n minus 1 times mu pi n minus 1 of t. So, we will have two terms in the right hand side coming from the one forward state or not moving from the same state. So, we will have two terms for j is equal to 1 to n minus 1. For the last state, that is the state 0, the systems come from the state 1. Since the state 0 is observing states, there is no second term. So, it is going to be mu times pi n of t. So, you know pi n of t, use the pi n of t in the equation for n minus 1 and get the pi n minus 1. Like that you find out till pi 1, use the pi 1 to get the pi 0 of t, use the recursive way. So, using the recursive way, you will get the pi j of t is equal to n c j combination n c j and e power minus mu times t power j. This is a survivable probability of system being in the state, and 1 minus e power minus mu of t n minus j. Suppose the system being in the state j, that means from the state n this many combination would have come, and the survivable probability is e power minus mu times t, and that power. So, this is nothing but the probability p power j and 1 minus p power n minus j. Therefore, this pi j follows a binomial distribution with the survivable probability e power minus mu t being in the state j. So, for the pure depth process, I have explained the time dependent probabilities of being in the state j, that is unconditional probability. So, with this the summary of this lecture is I have discussed the limiting, stationary and steady state distributions. I have introduced a birth death process, some important results also discussed, and at the end I have discussed the pure birth and pure death processes also. In the next lecture, I am going to explain the important pure birth process, that is a Poisson process, and these are all the reference books. Thanks.